And welcome back. We're going to be doing section 2.3 now. Not the derivative at a point, but the derivative at any point. Right? If given f of x, what's f prime of x? Not given f of x, what's f prime of 2? Right? So here's our first question. How would you find, algebraically, how would you find the derivative of x squared? First you have to do, what do you have to do? You have to use the definition of the derivative. So what is it? F prime of x equals what? Anybody? The limit as, what'd I do? Oh, whoops. The limit as what? H goes to 0. Or that was your delta t or delta x, right? Of the difference quotient. All right, so what's the numerator? F of x plus h. Wait, I'm doing this in general. Wait, you know, this tablet is acting weird today. I guess it doesn't like the air conditioning. I don't know, I use this all year long, right? But I'm never in a humongously hot room like this. I don't know, maybe it's the heat affecting it. All right, what else? Minus f of x, that's the difference part. Here's the quotient over h. Okay, now we want to rewrite this in terms of this f of x and see if we can find this limit algebraically. Now our aim here is to see if we can come up with some kind of a pattern for the derivative of x to the n. So I'm not just going to do x squared, I'm going to do x cubed, x fourth, x fifth, x negative 1, x negative 2, x to the 1/2, x to 1/3. Let's see what happens, okay? But let's start with this one. This is an easy case. So I'm going to find the limit as h goes to 0 of, all right, now what's the numerator? If I plug this into my function, x plus h all squared, okay. Minus what? Minus x squared over h. Okay, so the problem is that this is not a plug-in limit, because if you plug in h equals 0, what's wrong with that? You can't divide by 0, that's bad. Okay, but we want to try and manipulate this so we end up with another function with the same limit, but where you can actually plug in h is 0. All right, so suggestions based on your vast experience from yesterday. Foil it out. All right, do you know what the foiling of that is? What is it? Right. Maybe should we do it? I don't know. Maybe we should do it. All right, let's just do it on the side. You said x squared plus 2xh plus h squared. Let's just confirm that real fast for everybody. I got x plus h squared means x plus h times itself. All right, so x times x is x squared. X times h is hx. H times x is again hx. And h times h is h squared. All right, we call this FOIL a double distribution. Distribute the x twice, distribute the h twice. And yes, you do get 2xh or 2hx in the middle. All right, good. Let's go back and let's continue where we left off. So now we get the limit as h goes to 0 of x squared plus 2xh or 2hx, same thing, plus h squared, that's this piece, don't forget this piece, minus x squared all over h. Why is that helpful? Yes? Well, one thing at a time. The x squareds cancel, right? Okay. Trying to make this easy, guys. I don't want to go too fast, right? We're already going fast enough. All right, so the x squareds cancel. Show each step one step at a time. This is how you show your work. Limit as h goes to 0 of, what's left? 2xh plus h squared over h. All right, now what's nice about that? Again, it's still not a plug-in limit, but what's nice about it? Factor out the h as a common factor in the numerator. Well, since then it's multiplying, it'll be canceled by this h that's dividing. Let's show that step. Or you can simply divide it out. How do you divide a polynomial by a monomial? Divide each term by h, right? All right, so but let me just factor it out. H comes out, what's left? 2x plus h, and then over h. So now this h is dividing, this h is multiplying, they cancel, and we get the limit as h goes to 0 of 2x plus h, and that's a plug-in limit. If you plug in h equals 0, you get 2x. So the derivative of x squared is 2x. So now notice what's different here. I'm not getting a number. I'm getting a new function. This function describes all the numbers you would get, all the slopes of any tangent line along that curve. All right? Now, anyone have a problem actually doing that? Would you be able to do that? If I asked you to do that on Thursday, remember Thursday is our infamous test. Yeah, the party. Everyone gets a slice of the pie. What? Question?
How would you word that?
This is the question right here. That's the wording right there. I might be more verbal than that, but that boils down to that. I mean, find the derivative of f of x equals x squared algebraically, using the definition of the difference quotient. Part A, state the definition. Part B, apply the definition. Part C, find the limit. And that's one question. That could be one question. Yeah. Alrighty. Eventually it's going to get more interesting, all right? Each Thursday, another test, another chapter. Now, this week it's on chapter 2. Next week it's in chapter 3, but still stuff from chapter 2 is in there, right? The next week it's on chapter 4, but still stuff in chapter 3 and chapter 2. So the questions will get more and more applicable, more applications, real-world problems, get a little bit more interesting, okay? Now, if you take a look at the syllabus, week 1 is chapter 2, week 2 is chapter 3, week 3 is chapter 4, week 5 is chapter, week 4 is chapter 5, and week 5 is chapter 6. But we do a touch of chapter 7 also at the end, all right? So technically, it is 5 chapters in 5 weeks plus a touch of something else, okay? So you might say, okay, 6 chapters, because we do touch in chapter 7, all right? All right, so let's do that again for x cubed. And let's see if we can find some kind of a pattern going on so that in general, if I, one day say, look, I need the derivative of x to the 8th, what is it? Do you have to do it this way? Not necessarily. All right, so let's go on to my second example. Whoops, next page. What if, let's say, g of x is x cubed? Can you find g prime of x? Now, don't get all flustered that it's g instead of f, same difference. What does that mean? That means that g prime equals the limit as h goes to 0 of g of x plus h minus g of x all over h. I just wrote it in terms of a function called g instead of a function called f. No big deal. All right? But g is x cubed. So how do we write this in terms of the function x cubed? The limit as h goes to 0 of what? Well, what does this become? Just this. All right, so x plus h all cubed. Minus x cubed all over h. And so we want to expand this, right? Okay, let's do so. X plus h cubed equals, now let's see, do we know the binomial expansion theorem? Yeah. Well, how do you write that in general? I think it goes, right. If you do Pascal's triangle, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, we're interested in the one that has 3's in it, right? So you could say that it's x cubed plus 3, let's see, x squared h, okay, plus 3x h squared plus 1, plus this one, h cubed. I'm trying to think, how do you write that in general? You know sigma notation? Yeah. Yes. All right, let's see. N is 3. R is... Could I write this more in general? I'd like to be able to generalize this a little bit. Let's see. What if I said x plus h to the n is going to be the sum of NCR as R varies from 0 to n times x to the, let me think, R h to the R minus n. I think that's correct. All right. Does that notation look familiar at all? No? All right, let me explain what that means. If I wanted to find any power of a binomial, this is the binomial expansion theorem. It uses combinatoric numbers, combinations, permutations. You ever do that stuff in probability? These numbers, these are the numbers in Pascal's triangle. Okay? So what it means is, if I want to do, let's do an easy one. Let's say x plus h squared, which we already know the answer, right? Didn't we write this out a minute ago? X squared plus 2xh plus h squared, right? What does it mean? It says, take the sum as r goes from 0 to n is 2 of 2cr x to the r h to the r minus n. Or sorry, that's backwards. N minus r, sorry. Yeah, that's going to be n minus r. N minus r. What the heck does that mean? That means that you want to count r from 0 to 2 as integers, okay? So what are the r values? 0, 1, and 2. Okay. So I'm going to take a term when r is 0. I'm going to take another term when r is 1. I'm going to take another term when r is 2, and that's it. Now, do you know what this weird symbol means? Sum. That's a Greek letter sigma, S for sum. So take all the terms and add them up. That's what it means, all right? So what does it mean? Let r equal 0. So let r equal 0 everywhere. Oh, by the way, n is 2. Wherever I see n up here, right, it's 2 in this example, okay? So I'm going to say 2c0, x to the 0, h to the 2, because r is 0. So 2 minus 0 is 2. Plus, now r is 1. 2c1, x to the 1, h to the 1, because 2 minus 1 is 1. Plus, 2c, whoops, I wrote it backwards. 2c2, x to the 2, h to the what? 2 minus 2 is 0, exactly. Now, that looks like a lot of gobbledygook, but really it isn't. Because this is a number in Pascal's triangle, this is a number in Pascal's triangle, this is a number in Pascal's triangle. It's these numbers, 1, 2, 1. Okay, why? I'll show you in a second why. So this is 1. X, what's x to the 0? 1. And so 1 times h squared. Plus, what's this? That's the second number in that line in Pascal's triangle. Right, 2, x to the 1 means? X, h to the 1 means? H plus, and what was the last number in that line? 1 times x squared, and what's h to the 0? 1. Anything to the 0 is 1 except for 0 to the 0. We're going to get to that. All right, so what do you got? 1 times h squared plus 2xh plus 1 times x squared, and that's it. All right, so this works for any n. N could be 3, 4, 5, 6, 12, 5 million. I don't care. Yeah.
So the C0, C1, C2
Are the numbers from Pascal's triangle. But that happens to be a fluke, okay? This is what this, all right. If I let this be the n number, n equals 0, what row I'm in? N equals 1. The row here is n equals 2, which accordingly in the binomial expansion theorem has to do with the exponent. That's the line that we want, okay? And this is row n equals 3. If we call this column r equals 0, and this column r equals 1, and this column r equals 2, and this column, r equals 3, you see now that 2c0, 2c1, and 2c2 are these numbers right here. Where the first number is n, the row 2. The second number is the column 0, 1, and 2. Column 0, 1, and 2. But it's a fluke that this happens to be the case. Pascal's triangle comes up all over the place. This is really defined differently. This is defined based on factorials. You know what a factorial is? NCR equals n factorial over r factorial over n minus r factorial. So 2c0 means what? It means 2 factorial over 0 factorial over 2 minus 0 factorial. So what's 2 factorial over 2 factorial? What's anything divided by itself? 1. But wait, what about this? What's 0 factorial? It's not 0. What is it? It has to be 1. Why? Because otherwise this wouldn't work. When I do probability and discrete mathematics and stuff like that, this always comes up. 0 factorial equals 1 by definition. Who said so? God. Who's God? Blaise Pascal. Okay? Pascal said so. Okay? That's it. Alrighty. So 2c0 is 1. Okay, fine. What's 2c1? I know it's 2, but does it work out this way? Let's see. All right, okay, 2c1. All right, what do? This is the n value, right? So that goes on top, 2 factorial. This is the r value, right? So that goes to the bottom, 1 factorial. And this n minus r is 2 minus 1 is also 1 factorial. What does 2 factorial mean, by the way? I didn't even talk about that. Count down from 2 to 1, the integers, and those numbers, you multiply them together. So tell me, what's 3 factorial, for example? 6, right? Is everyone with me? 4 factorial? 24 and so forth, right? You good? Question? No? Okay. All right, so 2 factorial is 2 and 1 factorial? So 2 over 1 is 2. I'm getting that number, right? Okay. So how do you get this without FOIL? How did I get that? I said, okay, cubic means I'm in the third row. And I'm going to use the coefficients 1, 3, 3, 1. 3c0, 3c1, 3c2, 3c3. Okay? And then this is h0 x cubed, or h to the r, x to the n minus r. Right? So what was this? This was 3c0, h0, x to the 3 minus 0, or 3. Where does this come from? 3c1, x to the, I'm sorry, I'm doing h. H to the r, x to the n minus r. This is r, this is n minus r. 3 minus 1 is 2. Plus 3c2, h to the r, x to the n minus r. Isn't that what this is? That C32, that's this guy. C32. C31. C3C3. Okay? Plus 3C3, h to the r, x to the n minus r. Here's n, here's r. 3 minus 3 is 0. So you could write it out this way, or you can just look at this line right here. But that's where it's coming from. Okay? It's technically not Pascal's triangle. It's combinatorics. But, all right, whatever. So if that helps you FOIL stuff out fast, great. If it doesn't, well, too bad. So you could, yeah, you could do FOIL. But what if I asked you to do, you know, x plus h to the 10th? Could be. I would do it this way. You're welcome to do FOIL on 10 pages of paper.
What is this called?
This is called the binomial expansion theorem. Binomial expansion theorem. Look it up in any Algebra 2 text or pre-calc text.
You could just write out Pascal's triangle.
And basically use Pascal's triangle. Yeah, it gets a little weird if this number in front of the x is not 1 and this number in front of the h is not 1, but I'm not going to do that to you because the difference quotient always has x plus h in it, right? So if it's just 1x and 1h, it's very simple. If you have other coefficients running around here, the binomial expansion theorem gets really messy. I'm not going to get into that because we don't need to. Right. All right. So, and oh yeah, really? Okay. All right. So that means we can continue this question. Ta-da. All right. Wow. We did all of that to get to this point. Okay. So that was the limit as h goes to 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus this guy. So the idea is this: since all of these power functions I'm differentiating are based on that kind of an expansion, the binomial expansion theorem, they're all going to come up with some kind of pattern that's the same. And I want to try and see what that pattern is, okay? So I figured out if I start with x squared, the derivative is 2x. Now if I start off with x cubed, what's the derivative? All right. So how do you finish this up? Next step, what happens?
X cubed cancel out.
They're gone. Okay, good. So let's do that. We get the limit as h goes to 0 of 3x squared h plus 3x h squared plus h cubed. The x cubes are gone. Okay. Now what happens? Anybody? Yep. All right. Why don't I just divide it out? Can I just divide it out? Yeah. I wanted to make a big point that we're really factoring. Dividing and factoring are the same thing. But let's cut to the chase now. So if you divide the h into every one of these terms of this trinomial, what do you got left? 3x squared plus 3, whoa, ow, oh boy, YouTube, hang on. 3xh plus, there is one h left, right? Yeah, this is the one that went away. H to the 1, h to the 2, right? And now you can plug in h equals 0, right? This is a function whose limit exists at h equals 0. And so what do you get when you plug in h equals 0? You get 3x squared. Did anyone expect that? Does anyone already know the power rule? You've seen it, right? Is this consistent with the power rule that you know? Okay. All right, that's good. All right, so equals 3x squared. That's it. You're done. That's f prime, right. In other words, if f of x is x cubed, then, shut up. What are you doing? Then f prime of x is 3x squared. And you see the pattern already, right? So you take the exponent and you put it in front, and you take the exponent and you subtract 1 from it. Is that true? Let's look at what happened when we had x squared. All right, so what's my conclusion here? If f of x is x squared, then, what is it doing? Stop that. Then f prime is 2x. Now, is that the same pattern? What happened with the 2? It became the coefficient in front. What happened to the 2? What happened to the exponent? It's 1 less than the exponent was, right? So predict x to the 4th. What's the derivative? 4x cubed. Let's prove it. All right. All right, let's say one thing at a time. All right, so let's try this one. Let's say h of x. Well, that's probably not a good choice because I've got h's running around. Phi of x. I ran out of letters, so you ever take physics? When you run out of letters, you use Greek. Okay, so let phi of x equal x to the fourth. Question is, what's phi prime? It's just instead of f of x. I don't feel like writing f all the time. Okay, so first you write the definition of the derivative as the limit of the difference quotient. Then you apply it to this function. Then you simplify the limit, right? This is the process you should be getting used to in 2.3. That's what we're doing. All right, so we get that phi prime of x in general is going to be the limit as h goes to 0 of phi of x plus h minus phi of x all over h. All right, so let's write, that's in general for any function phi of x. Let's write this in particular for this particular function. So it's going to be the limit as h goes to 0 of, all right, now what's the numerator? X plus h to the fourth minus, what is that? X to the fourth all over h. And the idea is to simplify that. Use the binomial expansion theorem. Why FOIL 50,000 times? Okay, let's go back to Pascal's triangle. Well, okay, the question is, what's the next line? All right, you know what? I'm going to make a new scratch paper, okay? Here it is. All right, you tell me. 1, what's Pascal's triangle? 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Why? Because I could actually calculate it with factorials if I felt like it. 4c0, 4c1, 4c2, 4c3, 4c4. But I don't feel like it. Where did I get the 4 from? 3 plus 1. Where did I get the 6 from? 3 plus 3. Where did I get the 4 from? 1 plus 3. Where did I get the 1 from? 0 plus 1. Yeah. Okay. And that's the line I'm interested in because according to the binomial expansion theorem, if I'm doing to the fourth power, I want to be in the fourth row. Counting from 0, that's the fourth row. It's really the fifth row. All right, so can you tell me now what you would get if you FOILed out the whole damn thing? 1, I'm going to write it down. 1, what do you think? X to the fourth plus 4x cubed h, or hx cubed, I don't care, plus 6x squared h squared. Notice how the exponents always add up to 4. 1 plus 3, 2 plus 2, right? Plus 4x to the 1 times h cubed. Ugh. This is a function of heat. I've never had this happen. And one more term is simply what? H to the fourth, okay? So now you know how to FOIL real fast. I hate that. What is that? I'm going to have a problem with you. Ding, ding. Okay. Now this is remember, this is the simple case of the binomial expansion theorem, believe it or not. This is the simple case of the binomial expansion theorem. If we had other stuff going on in here, if it was something weird like, wake up, 2x minus 3h to the fourth, it would be much more complicated. Okay? I'm not doing that because it has nothing to do with the difference quotient definition of derivative. Yeah. Okay. Just so nobody's confused, what I'm doing is x plus h to the fourth, right? Okay. How do I get the exponents? Well, that came from this pattern over here. Okay? Notice this number, this is the exponent, right? For our purposes, that is a constant. So if this is 4, this is 4, this is 4, this is 4. What's varying is r. R counts from 0 to 4. So count. 0, 1, 2, 3, 4. Okay? So I get 5 terms. The first one is 4c0, x to the 0, h to the 4 minus 0. Actually, we did it backwards. That was the last term. Okay? Then R equals 1. 4c1, x to the 1, h to the 4 minus 1. Right? Then R is 2. 4c2, x to the 2, h to the 2 minus 2. Then R is 3. 4c3, x to the 3, h to the 4 minus 3. And then R is finally 4. 4c4, x to the 4, h to the 4 minus 4. Now the way we wrote it on the previous page, we actually did that in the exact opposite order, but it's the same thing. So why do we get those exponents? This is why. This is in general what happens when you FOIL. There's a generalization of FOILing at any power. That's why. I mean, that's a pattern. Okay. All right. So shall we use it? We didn't even get started yet. All right. All right. This is what we're doing, right? All right, let's make a little room. All right. So we get equals the limit as h goes to 0 of x to the 4th plus 4x cubed h plus 6x squared h squared plus 4x to the 1 h to the 3 plus h to the 4. That's this minus this all over h. Hoi. God bless. Okay. So now we end up with something actually familiar, right? Because you know what's going to happen next, don't you? Though what happens next? What? The x to the 4ths are going away, and then eventually the h's are going to cancel out, right? All right, one step at a time, so you don't put your foot in your mouth. Don't get too crazy. Limit as h goes to 0. X to the 4th is gone. I get 4x cubed h. Does that sound familiar? Didn't you tell me a minute ago that if the function is x to the 4th, the derivative is what? 4x cubed. That's where it's coming from. All right. Plus 6x squared h squared. This is going to drop out because the h is not going to cancel out completely here. When you plug in the 0, this drops out. All you're left with is this when the h is canceled. This is good. All right. Plus 4x h cubed plus h to the 4th all over h. What happens next? The h's cancel out. Right, let's divide everybody by h in the numerator. 4x cubed plus 6x squared h plus 4x h squared plus h cubed. And what happens when you plug in h equals 0? Everything drops out except for the first term, which is 4x cubed. Ta-da. Right? Is this getting obvious now? I hope. And now, if you don't like the binomial expansion theorem, knock yourself out. You can always FOIL. But otherwise, this process should be pretty obvious now. You guys who heard of the binomial expansion theorem before, whether it was called that or not? It may not have been called that, right? Okay. Because you really need to know how to FOIL high degrees. You know, it comes up a lot. So anyhow, so that's called algebra. You guys got to know some algebra, right? Did you guys do any like college algebra? Let's see, like in high school, sequential math 3, or math B, or algebra 2 and trig, or pre-calc in high school. They should all have something in there with this in it. No? Huh? Math B is very similar to pre-calc, yeah. Math B, or sequential math 3, or the new math B, or the newer algebra 2 and trig, or pre-calc if you took pre-calc. Somewhere in there you should have seen that. All right. Okay, that's enough for n is an integer. What if n is negative? Oh, sorry, a positive integer. What if it's a negative integer? That's different. Let's try again. All right, but wait. Did I summarize it? I didn't summarize it. Let me summarize what we got. So if f of x is x to the fourth, that implies that f prime of x is 4x cubed. So can you generalize this? What do you think if f of x is x to an integer n? Then f prime of x, what do you think it is? nx to the n minus 1. Is that true for all n's? For any n in integer? We showed it pretty much. We didn't prove it for every single n on the plane, but we showed it pretty much for positive integers, right? What about for a negative integer? Is it going to work? What if n is like negative 1? Let's predict. I'm going to do it the hard way, okay? But what does this pattern say? If n is negative 1, x is by the way, what does x to negative 1 really mean? It means 1 over x, right? So the derivative of 1 over x, according to this, would be what? Or x to the negative 1 would be what? Negative 1 times x to the negative 2, right? So you should get negative 1 over x squared. Let's see if that's true. So this is supposedly the power rule for differentiation, the derivative of a power function, any function of this form. Now let's see if it's true. I don't know. I've shown it seems to be right for positive integers. Let's see if it's true for negative integers. So let's try this. What if f of x is x to the negative 1? So n is negative now. Okay. Question is, what's f prime? And you said according to that pattern, it should be negative x to the negative 2 or negative 1 over x squared, right? Let's see if we can demonstrate that using the definition of the derivative that we know. All right. That's the game today. Now, I know today's topic is 2, 3, 2, 4, 2, 5. I want to really spend a lot of time on 2, 3 because people get stuck here. I will get to 2, 4, 2, 5. I don't know if I'm going to record it. Maybe a little bit of 2, 5. Well, we'll get to that. All right, so we're still in 2, 3. Finding the derivative function. All right, so f prime is the limit as h goes to 0 of f of x plus h minus f of x all over h. So in terms of this function, by the way, remember this is 1 over x, right? So I'm going to write it that way. The limit as h goes to 0 of 1 over what? X plus h. Minus what? 1 over x. All over what? H. Now we encountered something like this yesterday. They gave us x to the negative 2, and they wanted you to find the derivative at x equals like 5 or something, right? So we've stumbled on this a little bit before. What's your intuition here as to the next step in simplifying this limit? Because we already saw one like this, sort of. Get a common denominator, right? Okay, good. All right, so we're dealing with fractions. We're subtracting fractions. How about a common denominator? So name the common denominator forget this h here. Name the common denominator for this difference up here. X plus h times x, right? All right, they don't have any factors in common, so just multiply them together. So the greatest common factor, or the least common factor, I should say, should be this times this. So multiply top and bottom by x. So I get x over x times x plus h minus. Multiply top and bottom by x plus h. So I get x plus h over x times x plus h. So do you have a common denominator? So can you subtract? How do you subtract two fractions of the same denominator? Just subtract the numerators and keep the denominator. All right. So what is x minus x plus h? Not h. Negative h, isn't it? Right? Because how do you subtract? You add the opposite. I'm adding a negative x, cancels that x. I'm adding a negative h. Remember, there's no such thing as subtracting. Subtracting is adding the opposite. There's no such thing as multiplying. Multiplying is adding a bunch of times. There's no such thing as dividing. Dividing is multiplying by the reciprocal, and multiplying is adding a whole bunch of times. All right? Or dividing is subtracting a whole bunch of times. There's no such thing as subtracting. Subtracting is adding the opposite. Okay? There's only one operator, addition. Okay? So rewrite everything in terms of addition. This is x plus negative x minus h. Okay? So what do I get? The limit as h goes to 0 of negative h over the common denominator over h. Now remember, we came up with this problem yesterday. How am I going to divide this fraction by h? Yeah, this is another fraction, h over 1. How do you divide by a fraction? Multiply the reciprocal. How about we just write it that way and cut to the chase already? So I'm multiplying this fraction times this fraction. How do you multiply fractions? Multiply the numerator times the numerator, the denominator times the denominator. But if stuff cancels, you can make life easy. Is there anything in the numerator that cancels with anything in the denominator? The h's. H into negative h is just negative 1. All right, so I get the limit as h goes to 0 of negative 1 over x times x plus h. Now notice, even at this point, this is not a plug-in limit, because if you plug in 0 for h, you're screwed. Technical term. Look in the glossary. Screwed. All right? You can't do it. But here, what if you plug in h equals 0 here? It's okay, because 0 plus x is x, and x times x is x squared. So you get negative 1 over x squared, which is what we said it would be. Negative 1x to the negative 2. So that power rule seems to work for negative exponents too, huh? All right, so we're sort of demonstrating. We're taking particular values of n. We didn't prove it for every single value of n. That's way beyond the scope of this course. We can't do that. But we're getting an idea that this pattern is working. Let's extend it further. What if the exponent is not even an integer? What if it's a fraction? What if it's like x to the 1/2? What does x to the 1/2 mean? Square root function, right? All right, let's try that. Now, all right, wait. Let's write our little conclusion, right? If f of x is x to the negative 1, then f prime of x was indeed negative 1 times x to the negative 2, like we said, right? All right, what if it's 1/2? What would you get over here, do you think? What goes here? 1/2, what goes here? Not 3/2, careful. Negative 1/2. Right? Remember, we said if f of x is x to the n, then the derivative, apparently, f prime, is n times x to the n minus 1. So if this is 1/2, this is 1/2. If this is 1/2, this is 1/2 minus 1, which is negative 1/2, right? So you would expect, all right, so this is the question. If f of x is x to the 1/2 or rad x, well, let's make it x to the 1/2. If f of x is x to the 1/2, you would expect the derivative to be 1/2 x to the negative 1/2. In other words, the derivative of the square root function should be, shut up, one over 2 rad x, if you want to write it in radical notation, right? Let's see if that's true. That's my guess. That's my, my prediction, my hypothesis. Let's prove it. All right. So just to be fun, I'm going to go red. I'm going to call it g. Let g of x equal x to the 1/2. Find g prime. All right, what's the definition of the derivative for g prime then? In general, for any g, the limit as h approaches 0 of, what's in the numerator? In general, any g. G of x plus h minus g of x all over h, right? Now let's do it for this g. Okay. The limit as h goes to 0 of rad, I'm going to write it in radical terms, x plus h minus rad x all over h. You're going to find it's going to be easier to deal with it in radicals, in terms of radicals, okay? All right, now, Can you simplify that limit? Algebraically, so that it's a plug-in limit for h equals 0. If you square both sides, what, top and bottom you mean? Or we square, yeah, you're going to change the problem. I don't want to change the problem. I want to be able to say this line equals the next line equals the next line equals the next line. If I actually square, just square, it's going to change the problem. Notice what we've been doing up to now. We've been multiplying by 1. We've been canceling out to zeros, right? Opposites cancel. I want to keep to that. Is there some way to simplify this without changing the value of the function? I want it to behave the same way. It's just I want it to be defined at h equals 0. Has anyone heard of, any ideas? No? Has anyone heard of conjugates? What's a conjugate? The opposite? Not exactly the opposite. Right. If you take the conjugate of the numerator and you multiply top and bottom by that, you're going to find a much simpler expression. Now notice all we're doing is multiplying by 1. That's legal, right? If you multiply by 1, does anything change? No. 1 times anything is the same thing. All right, so what I'm saying is I'm going to take this expression. I'm going to multiply the top and the bottom of this by the conjugate of the numerator. The idea being that that's going to simplify my radicals. You'll see. If you've ever encountered conjugates before, this is obvious. This is a way to simplify radicals. If you've never seen conjugates before, this would not be obvious. You guys have to have a little algebra under your belts. I don't know. This is the conjugate. Now, can I just multiply the top by that? No. I'm going to multiply top and bottom by that because I'm really then multiplying by 1. Okay. Now, the first place you actually encounter conjugates is in complex numbers. Anyone deal with complex numbers before? 1 plus I, 1 plus or minus I, 1 minus 2I, 3 plus 2I, that stuff. Right? I is, anyone hear of I before? The special number? Square root of negative 1. Okay. Which is called imaginary, and that's bad because it's not. It really has a real effect on mechanical engineering problems, but we'll get to that. All right, so let's FOIL this out. Basically, that's what we're doing. We're going to FOIL this out. All righty. All right, so let's get the limit as h goes to 0. And let's just FOIL the numerator, right? So first times first. What's radical x plus h times itself? X plus h, right. Okay. Well, technically, if you square a radical, you get the absolute value. But let's assume that these numbers are positive for the moment. I don't want to get crazy with domain problems right now. So first times first, outer times outer, you're going to get, well, let's write it out. Rad x times rad x plus h, whatever the heck that is. So I distributed this twice. Now I've got to distribute this twice, right? So what's this times this? The same thing but negative, right? So negative rad x times rad x plus h. So do I really care what this is? Because why? It's going to cancel out. And then negative rad x times negative rad x, negative rad x times positive rad x is negative x. All over, what happens if you multiply the denominators? Remember, you know how to multiply a fraction times a fraction, right? Numerator times numerator, denominator times denominator, unless things reduce or something first. Okay? So I'm going to multiply this whole mess times h. H times mess. Mess is another technical term. Look it up in the glossary. It means I'm too lazy to say what the hell it is. So do you see anything nice happening here? What would be nice? What? The x's are going. Goodbye. And we already said this stuff is going too, right? So what the heck is left? Just h. Okay. In the numerator, I'm saying. So the limit, as h goes to 0, the numerator is just h. That was nice. Didn't that simplify nicely? All over the denominator, which is h times this mess. But notice this h is multiplying. So it cancels, because this is like, the opposite of dividing. It's up here. So they're going to cancel. And I get 1 over the mess. But guess what? Now you can plug in an h equals 0, can't you? So, all right, so again, what is 0 plus x? X. What's rad x plus rad x? 2 rad x. So in the limit, 1 over 2 rad x is what you get. And isn't that what we expected? Using the power rule. I just plugged in h equals 0. And so I got rad x plus rad x is 2 of them. Combining like terms, that's all. Okay. So we were correct. Our assumption back here, our hypothesis, did we do it on this page? Right, was that we were going to get 1 over 2 rad x, or 1 half times x to the negative 1 half. Same thing, right? You could write it in terms of fractional exponents, or you could write it in terms of radicals. It's the same result. All right, so it seems that we're going to be able to adopt this power rule thing, okay? Let's say that the derivative of x to the n is n times x to the n minus 1, as long as n is an integer or a rational number, a fraction. It could be proven also for irrational numbers, any real number n, okay? I don't know about any other kinds of n's, like if n is imaginary or complex, that's another story. Okay, let's not go there yet. All right, so that's it for 2.3. Any questions on 2.3? Okay. Now, the idea here isn't really what's the power rule for differentiation. The idea here is, can you find the derivative of a function algebraically, no matter what that function is? We're eventually going to do the same thing for sine, cosine, and tangent, for log base 10, log base e, for 2 to the x and e to the x and 3 to the x, for any function you feel like. And once you get the derivatives, you can get the antiderivatives. Chapters 2, 3, and 4 are differentiation. Chapters 4, 5, 6, and 7 are anti-differentiation. Aha. And they go hand in hand. And you're going to see that's a very interesting result. We're going to get to that. All right, so that's it for 2.3. I'm going to skip 2.4 for now because it just has to do really with a pre-calculus topic of functional notation. We'll get back to that when we need it. Take a look at 2.5. What does f prime mean? What does f double prime mean? Okay, that's really what 2.5 is. And in the remaining 8 minutes, I'm going to let YouTube in on a secret too. All right. Do you know what it means when your function's derivative is positive? The tangent lines have positive slopes. Doesn't that mean the function itself must be increasing? Do you know what it means when f prime is negative? The tangent line slopes have negative slopes. But the curve, for it to have negative tangent line slopes, the curve has to be decreasing. Right? The y values have to be decreasing. Do you know what it means when f double prime is positive? Let's combine all of these. Let's do all the combinations. F prime is positive. F double prime is positive. F prime is positive. F double prime is negative. F prime is negative. F double prime is positive. F prime is negative. F double prime is negative. What kind of curve would have these properties? Each one of these 4 lines is a separate curve I'm describing, okay? So if my function is increasing and at an increasing rate, in other words, if the slopes of the tangent lines are positive, but they're getting more and more positive, what does the curve look like? It could be some kind of a it could be hyperbolic, but what piece of the hyperbole are you talking about? I'm talking about a function whose y values, as x increases from left to right, what are the y values doing? They're increasing at an increasing rate. They're increasing at a decreasing rate. The rate of increase of f prime is negative. F double prime is the rate of increase or the rate of change of f prime. By the way, if you work for NASA, we have names for this stuff, okay? If f is your displacement function, how far away you are from your starting point, right? Distance from home, say, right? F is your displacement displacement. F prime is your velocity. F double prime, the rate of increase or the rate of change of your velocity would be called the acceleration. F triple prime, if F is your displacement, your position, F prime is your velocity, F double prime is your acceleration, F triple prime is the jerk. I kid you not. I once avoided getting a ticket by explaining to a cop what the jerk was. Okay? I said, from now on, you can give a ticket if the following is true. Okay? So he was going to give me a ticket because I didn't stop at the stop sign in the middle of this place, in the middle of nowhere in Syosset. Like in some residential area. I never saw the stop sign before. He probably just put it there for the day, okay? So I almost didn't stop, but then I stopped. And I said to the officer, I said, look, you know that the car stops if your body jerks. Okay? In other words, the rate of increase of your acceleration is itself decreasing. No? All right. Let's say you're driving down the highway. You're going, speed limit, 55 miles an hour. And some jerk, pun intended, cuts you off. What do? You slam on the brakes, right? Now, what do you feel? If you're driving at a constant rate, a constant 55 miles per hour, you don't really feel the velocity. You feel acceleration. You feel the change in the velocity. So when you hit the brakes or you hit the gas, you feel the force changing on your body. You feel the acceleration. But if then, say, all right, let's put it this way. Say you're 55 miles an hour. Then you start trying to pass somebody. What's going to happen? You're hitting the gas, right? So you're accelerating. Your velocity is increasing. Then some jerk cuts you off. What are you going to do? You're going to slam on the brakes, and your body jerks, right? That's the third derivative. You ever see on Channel 12, they have those high schools competing against each other sometimes? Some kind of... Yeah, what is it called?
Challenge.
Long Island Challenge, right, okay. One year, I got 3 minutes left. One year, I remember my school got on there. And in those days, they had 4 kids on each team, but the teams were bigger, so the other kids formed the audience, right? And I have this on video somewhere. I got to get it, put it on YouTube. And we were playing, I don't know, Oceanside, right? My school's Boulder. So what did the kids in the audience do? They made up signs, like cheerleading, right? And one of the signs said, Oceanside equals F triple prime. And it got on TV because News 12 didn't know what the heck they were doing. They were calling the Oceanside team a bunch of jerks. Yes, there you go. Okay. So if S is your displacement, S prime is your velocity, S double prime is your acceleration, S triple prime is your jerk, believe it or not, F quadruple prime is your snap, quintuple prime is your crackle, and sextuple prime is your pop. I kid you not. The specs for building the space shuttle involved a jerkometer. There's such a thing. The jerkometer had to have a very small reading on the wing vibrations. I kid you not. Worked for NASA, believe it. You're going to just see stuff like this, okay? So if the function is increasing at an increasing rate, it's going to look like this. Because the slopes of the tangent lines are positive, but they're getting more and more positive. If it's increasing at a decreasing rate, it's going to look like this. So the slopes of the tangent lines are positive, but they're getting less and less positive. If the function is increasing at decreasing at an increasing rate, it's going to look like this. The slopes are negative, the tangent lines are negative, they're getting less and less negative. Negative 2, negative 1, negative 1/2. It's getting closer to like 0. Right? Less and less negative, more and more closer to positive. And if the function is decreasing at a decreasing rate, it's going to look like that. In other words, the slopes are going to get more and more negative. So negative 1, negative 2, negative 3 slopes. Right? The slopes are negative, they're getting more and more negative. The slopes are negative, they're getting less and less negative. The slopes are positive, they're getting less and less positive. The slopes are positive. They're getting more and more